Good morning, everyone. Welcome back to Historical Geology 1404. I greet you from my throne of exam reviewness, because that is what we have today. Today is our exam 2 review. I hope you don't mind. I've been running late. I was in the office until 2 a.m. last night doing homework for my PhD. So I'm going to be snacking on some dry granola for breakfast while we talk today, if you don't mind. Well, let's start off with what's going on.
Well, Pope just died.
The Pope just died.
Did?
He did. Just passed away. Last night, I believe, early in the morning, right?
Oh, in the morning.
No. Yeah. Any Catholics in here? Couple? Okay. I'm not personally Catholic. I do think that this Pope was a very good man, though. So, he seemed to do some good things, seemed to care about people. It's a loss. I'm sorry for it. All right. Anything else? Did I already tell you about what's going on in Alaska, Anchorage? Yep, Mount Spur, which is not far from Anchorage, Alaska, has been indicating it may erupt soon, and they evacuated about 300,000 people from the area last week. I haven't checked the news today, but I haven't gotten an eruption warning from the USGS, so I guess nothing's happened yet. I don't know if they've let people start going back or if the signals have started dying down or not. They'll typically give it a little bit of time before they let people start going back. What else?
You know about that planet they've been talking about, saying it might have life called K2, might it be?
Life on K2?
Might it be, yeah, a planet they say it's kind of like Earth.
A planet that's living on K2, like high up on the slopes?
It's a planet called K2.
Oh, it's a planet called K2. We're not talking about the mountain K2.
No.
Oh, okay. K2 is a mountain in the Himalayas, one of the tallest ones. It's not quite as tall as Everest, but it's up there. Sorry, I thought you were talking about a plant that was living on K2. So tell me about this plant that is called K2.
It's discovered by the Webb's Space Telescope and satellite, the Webb.
Discovered by it? Where?
Well, they looked through the planet and they through that sun's atmosphere, they found gases like methane and carbon dioxide on that planet.
Oh, it's a planet. Oh, I can't hear you very well today, I guess. Sorry about that. So there's a planet called K2 that may have life.
Because of the gases they discovered on that from the atmosphere.
You said methane and what?
Carbon dioxide.
Carbon dioxide? Yeah, I mean, those are greenhouse gases. Those can be made inorganically. But do you remember the 1958 experiment I told you about? The Miller-Urey experiment that we mentioned last week? Where they basically took all of these gases and combined them into a self-contained vessel and then added an electric charge. And all of a sudden, there were organic compounds everywhere, including amino acids, which are the building blocks of our DNA. Remember I told you about that? An environment like that is primed for starting off making those organic compounds. So it's entirely likely that if the atmosphere has those compounds, and all it takes is a static charge to make, say, a lightning bolt, right? It's highly likely that there are organic compounds like amino acids forming on the surface of that world, or even in the atmosphere, which means that some form of life proximal to our own could be possibly happening there, which is very cool. Where is this planet?
It's in the Leo star system.
Leo.
They say it's orbiting a dwarf planet, a dwarf star,
A dwarf star.
and they say it's in a habitable zone.
Yeah. Dwarf stars are exactly what they sound like. They're tiny. They're very small. Okay. Very interesting. I don't remember how far away Leo is.
It says about 124 light years.
124. Okay, so a little out of reach. Yeah. Far more likely that we'll get to Betelgeuse. I think Betelgeuse is the closest one. Tau Ceti. Tau Ceti is pretty close. Far more likely we'll get to those one day than somewhere like that.
And it
Although, so what?
says, they say that it'll take them like a year to like fully like make sure that the data is like correct.
Yeah, you want to collect data for as long as you can before you make a hypothesis. This is true. Okay. Cool. Thank you for sharing. What else? Any other interesting questions? No? Well, then let's talk about exam 2. Exam 2 covers module 2, lectures 9, 10, 11, and 12. No, hold on. Lectures 5, 6, 7, and 8. I was, for some reason, thinking about 1403. 5, 6, 7, and 8. Diversity of life, correlation of the fossil record, evolution, adaptation, mutation, DNA, life on other worlds, all of that. Fossils, how we name them, how we differentiate geological time and the layers of rock to those times. All of these are subjects that are fair game for the exam. Okay? So just the last 4 lectures that we've gone over. The exam's going to be 20 questions or less. So I won't tell you exactly how many. It will be 20 questions or less, just like exam 1. All the usual suspects: short answer, multiple choice, true, false. You know the drill. You will have 500 minutes to take it. Should be more than enough time, right? You cannot discuss any of the questions with each other. You cannot work on them together. Please refrain from using online resources. This includes AI, because more often than not, you'll get the answer wrong. And this is why. The AI and Google, neither of them have any context for what we have talked about in this class. So just like when I told you what the definition of a mineral was, and I gave you a word-for-word definition of a mineral as it matters in this class, if you were to go to Google and Google the definition of a mineral, it would be a little off from the one I gave you. And that's how I would know, okay, they went to Google for that, right? And I've caught plenty of people doing that. It's tempting, but neither AIs or Google searches have any context for what we have talked about in this class. And so going there for answers will not benefit you, I would say. Let's see, what else? Oh, I'm going to have it close on Tuesday night. So you'll have it open for 2 days, okay? Kind of a day and a half, actually, because I want to have it over and done with by the time we meet together again the next time on Wednesday, so that maybe we can discuss questions you might have about it, or at the very least, not have to worry about exam 2 while we're starting to learn the material for exam 3. Okay, so it's going to close Tuesday night, probably about midnight is when I'll have it. I think I already have it set up for that, but I'll check here at the end of the review and make sure that's when it's due. Any questions about the format of the exam? No? Okay. Well, then let's move into the content. Are there any questions about the content? I know that I got a few emails from online students earlier this morning, but I haven't checked them yet to see if they were questions. Let's look. While I'm bringing this up, you guys can for sure ask your own questions, though.
Do you have to identify fossils on the exam?
Great question. This is not a lab exam. However, even though we've been talking about fossils in labs, we have also been discussing fossils in lecture. So while I won't do something like, say, here are 5 samples in hard copy, tell me what they are, I might show you a picture and ask a general question of, what kind of organism is this, right? Is this a fish? I mean, something like that. I'm trying not to give you an exact example of what's going to be on there, but something like that, right? We're asking you to give me a general description of what kind of life it is, because that is very relevant to what we have discussed so far and will continue to be relevant through Module 3. Speaking of lab exam, we'll probably have lab exam in 2 weeks. No, that won't work. I really don't like semesters where they started on a Tuesday. Because if it starts on a Monday every time, then both the Monday, Wednesday, and the Tuesday, Thursday classes are on the same track. But when they started on a Tuesday, the Monday, Wednesday classes get thrown off hard. And I effectively lose 1 day because graduation doesn't move. So, unfortunately, what that means is this semester you might have to take the final exam and the lab exam in the same week, which sucks for everyone, but there's not really a way around it with the math because you don't get all the material that you need for the lab exam until the end of the last lecture. But we'll cross that bridge when we get to it. For now, let's just focus on this one. Okay, so I'm going to keep going through these and seeing if anyone has submitted any questions here.
What are the different families of life?
There are so many families.
What's more broader?
Right, you've got kingdom, phylum, order, class. You guys, what do you call it when you come up with a...
Acronym?
Huh? Not an acronym, but you're following the same line of thought that I am. Where you come up with like a rhyme, right? No, a rhyme to help you remember something. Not a simile. A simile is something like an analogy. Mnemonic. That's what it's called. Okay. Ready? Dear King Philip came over for good soup. This is the most PG version that I've heard. There are some pretty bad ones. Okay. Dear King Philip came over for good soup. Domain, kingdom, phylum, class, order, family, genus, species.
Filipino children. Friday, going south.
Might not be a bad thing to write down.
I remember it. But that's how I remember it.
Oh.
Sorry, what?
Made us make our own acronym.
Oh, yes, you italicize species. You don't italicize any of the other designations except the genus and species combination.
Why are those italicized?
Tradition. There are a lot of things in science that really only happen because that's just the way that they were and that's the way that they continue to be. Why do we call, actually, I haven't explained this to you yet. There are two broad classifications of dinosaurs, Ornithischian and Saurischian. Okay? Ornischian dinosaur hips look like lizards. Saurischian dinosaur hips look like birds. And yet, the Saurischian dinosaurs are named Saurischian, which means lizard-hipped. And it's only because the guy that first found them and identified, those kind of look like birds right there. Right? That's almost like a bird-like structure. And so he named them Ornischian. Whereas later on, people found Saurischian dinosaurs like, that actually looks a lot more like it. And yet no one changed it. And so the lizard-hipped dinosaurs are the ones that look more like birds. As a matter of fact, birds are in Saurischia. Birds are in the group of lizard-hipped dinosaurs. Everything would be thrown off if we switched it around. So no one ever has. It's just the way it is in science sometimes. Maybe someone will do it one day. Maybe the scientific community of the world say, okay, this is too confusing. Let's change it. I don't think it'll ever happen. Okay. I went camping over the weekend, so I got bombarded by emails. I'm just going to keep going through these looking for questions while you guys come up with new ones. Oh, whoops. No. What else? Hit me. You guys really understand mutations and adaptation that well? That's impressive.
Or is it the environment changes? And the mutations are just genetic mutations that happen.
This is a great question. Cause and effect. We like to think of things in terms of cause and effect, right? I pick this up, I drop it, it fell. I did a thing, I made an action, a consequence resulted. Cause and effect. But mutation isn't really a cause and effect thing. A change in the environment is not prompting a mutation. These mutations are constantly happening anyway. So, that being the case, a change in the environment is simply changing the set of parameters by which a set of mutations would be positive or negative. Right? You remember when I told you about the tuskless elephants? Yeah, that's an interesting one, huh? In a world without humans, hunting elephants for their tusks, how much advantage is an elephant without tusks? None. And it would die off quick. So the random mutation causing an elephant to have no tusks is positive or negative based upon its environmental factors. The presence of humans did not make that mutation happen. Who knows how many times in the past that mutation has already happened, randomly. I mean, the statistical likelihood of it is really low, but it's possible. There are so many possible iterations of mutations that it's unlikely that any of them repeat, at least not often. But regardless of that fact, Only the fact that humans are here made it positive. Now, if mutations are random and environmental changes, I mean, some of them can be random. They're caused by processes, right? They're not truly random. They often happen in cycles. Then there is no cause and effect in this sequence, okay? There is only change and possible changes, right? Just like an animal can't decide, I'm going to mutate now, the environment can't speak to the DNA of an animal and say, hey, change this way. Did that answer your question? No?
Yeah.
Oh, okay, good. I'm sorry, I'm having a problem hearing today. There was a crazy windstorm out where I was camping. I was out on the other side of Stanton. We had gusts at 50 miles an hour on Friday night. Yeah. A couple of the other tents for the group that I was with, their tent poles snapped in half, like the metal tent poles, not like the plastic fiberglass ones that slip into each other. They were metal tent poles, and they got snapped in half. The tents fell down. It was loud. I barely got any sleep because it was so loud. I don't know if that's part of why I'm having a hard time hearing today or what, but I'm having a hard time for some reason. Might be all the dust that's in my ear still too. Sorry. What else?
All right, question.
Yeah.
Is life possible on gas planets?
Oh, this is a great question. Is life possible on gas planets? Name a gas planet for me.
Jupiter.
Jupiter, great. Is life possible on Jupiter? Why not? Right? Jupiter is filled with hydrogen and methane and other gases that are necessary for to start that process of life. The reason why we call them a gas giant is because, as far as we can tell, it's just a bunch of gases. But logically, that can't be the case. There has to be a core of some kind, around which all those gases have coalesced and have been drawn together by the gravity of that object. We can't prove it because we can't get enough instruments to penetrate the gases of Jupiter, and we've tried. But we believe that there is a planetary body at the center of Jupiter, at the very least the size of Earth. Now, what would conditions be like on that planet? Incredibly hostile. I'm talking gravitational forces that would squish a submarine to the size of a soda can, right? We've already got forces almost that powerful at the center of our planet, right? Heck, go to the bottom of the Mariana Trench and it'll still squish a submarine flat. Maybe not that flat, right? But Jupiter, what could possibly live on the surface of that? Don't know. But what about the clouds? Right? In a planet where the atmosphere is almost as dense as our oceans. It's gas, bear in mind. It's just very dense gas. So with an atmosphere almost as dense as an ocean, who's to say that those amino acids can't form and bond? Who's to say that some other combination of proteins could not form similar structures like DNA? There's nothing to say it can't. Matter of fact, if life can start in our oceans here, it is very likely that life could start there. Here's the kicker, though. Here's the interesting bit. Jupiter, you notice how it has those bands of color? Those bands of color represent different concentrations of gases in the outermost layer. But there's also different gas layers the deeper you go. Just like in our atmosphere, how we've got a lot of light nitrogen-bearing gases at the top, and then we've got a lot of oxygen and carbon dioxide things closer to the surface. Just like that, Jupiter has stratifications within its atmosphere, where you've got certain gases here, and then here, and then here, and then here. So within Jupiter's atmosphere, based upon our experiments and the math people have run over and over and over, there must be a layer of gases in Jupiter's atmosphere that is oxygen and water rich. Life like ours could survive in there. Theoretically, we could fly into Jupiter's atmosphere, and then once we reach that layer, just open the window, right? It is theoretically possible that once we get deep enough into Jupiter's atmosphere to where we reach the oxygen and water vapor layer, you could literally just open the window and breathe that atmosphere. Maybe one day there will be space stations or something just sitting 5 or 6 kilometers into Jupiter's atmosphere in the oxygen layer, and people can live there. A very interesting prospect, no? Is it really windy? Yes. Matter of fact, have you ever looked at a picture of Jupiter and seen what they call the Great Spot? That is a megastorm, a storm that you could fit, I forget how many Earths in there, but it's a storm larger than, I'm just gonna give a safe estimate, a dozen Earths, right? And it makes its way around the planet. As far as we could tell, it's been doing that forever. We don't know exactly what it was that set it off, but there's a possibility that it happened from a large impact. We've recorded comets striking Jupiter. Like, obviously it's not a hard surface, but they fall into Jupiter, and I'm assuming that they hit whatever's in the middle of it. But as they go through the atmosphere, they cause a swirl in the gases, similar to the motion of the Great Spot storm. It's possible that a massive collision or a near collision from a larger gravitational force than a comet could have caused the sort of swirl that helped make the Great Spot. Also likely that it's due to gravitational pull from the sun, or a combination of the two. The Great Spot? I don't actually know. I don't know enough about the Great Spot to know if it's shrinking or not. I haven't looked into it that much. Alan looks like he's doing some research, though. The conditions for life. Fantastic. Well, conditions for life or the conditions for our life? Okay, well, life in general is a very interesting question. We thought that we knew the answer to that question. This Goldilocks zone. You remember I told you about the Goldilocks zone around a planet? What are the characteristics of a Goldilocks zone?
Not too hot, not too cold.
Not too hot, not too cold. You remember we did this retelling of the Goldilocks and the Three Bears? Wasn't that fun? Okay, so not too hot, not too cold. What else? What did Goldilocks say about the bears' beds? Not too, well, I think it was not too big, not too small for the beds, right? Or maybe it was the chairs. Maybe it's the chairs I'm thinking about. This chair is too big, this chair is too small. This one's just right. I think the bed was not too hard, not too soft, right? So just like Goldilocks going through over and over and over these things and be like, this one's too much this way, this one's too much that way. The distance from our star, the characteristics of our planet, how big our star is and what kind of star is, all of these things go into making the Goldilocks zone. What happens if we're too close to our star? Too hot for what?
As far as you can tell.
Well, we're not there. We don't have life yet. We're talking about what could make life.
Water.
Water. If we're too close to the star and it's too hot, what will water do?
Evaporate.
Mm-hmm. You won't have any liquid water. But if we're too far from the star, what happens?
You freeze.
The water will freeze, and we will still have no liquid water. Okay, what happens if our planet is too big?
That is too.
Gravity will be incredibly stronger, very much stronger, which will affect the atmosphere that we have. Atmosphere will be much closer to the planet's surface and be a lot denser. What if we're too small? Yeah, there isn't enough gravity to keep the atmosphere here, and it all drifts away, right? Okay, so what we're piecing together here is that, and this was the traditional belief, that there was a very finite zone from the distance of your star where you have liquid water and within which the planets are the right size for life to exist. Life as we know it now, as you and I have come from, as you and I are at this moment. Relying on this careful balance of temperature between 0 and 100 degrees Celsius, at which water is where we need it to be. 0 degrees Celsius, it freezes. 100 degrees Celsius, it boils, right? This 100 degree zone, we call that the Goldilocks zone. We are inside the Goldilocks zone, a little bit closer to the warmer end. Whereas Venus is just barely outside the Goldilocks zone. Actually, no, it's barely inside the Goldilocks zone, I believe, on the hot end. And Mars is in the Goldilocks zone, but well into the cool end. Okay? In this band of distance from the sun. There are plenty of planets we can see out there within the Goldilocks zone, but there are a heck of a lot more that are outside of it. So now let's talk about what people are starting to think. People held for a long time that the Goldilocks zone was the only place that life could exist in. But that can't be true. And there's evidence for it here on Earth. For example, the extremophile bacteria that I told you all about, right? Do y'all remember that extremophile bacteria? In what conditions can extremophile bacteria live on Earth?
Anywhere.
All right, but can you name a few that they do?
Thermal vents at the bottom of the ocean.
Hydrothermal vents. Boiling water. But also frigid temperatures at the bottom of the ocean. Right? No sunlight. No need for photosynthesis. Life can exist there in those conditions, having never seen the sun. Why can't it live somewhere else in similarly hostile conditions? Like under 15 kilometers of ice on Enceladus or Titan or Europa. Or a dozen kilometers into the gas clouds of Jupiter. Understanding more about how the extreme forms of life on our planet have developed, which, by the way, are also the most ancient forms of life. This extremophile bacteria, as far as we can tell, is extremely closely related. It has not changed much since early forms of life on Earth. If early forms of life on Earth were able to develop in hostile environments and still live in those hostile environments, that opens the Goldilocks zone to be much larger, much wider than we previously thought it to be. There are bacterial colonies living in rock 10 kilometers below our surface right now. There are bacterial colonies living in the coldest temperatures on Earth. There are tardigrades on the moon. All right? I told you about that. Life can exist in a lot more places than we previously thought. And only in the last few decades are we actually really, truly understanding that. So, What are the conditions for life to exist? Where can life exist? Maybe anywhere. There might be life everywhere. But here's the kicker. Intelligent life. Let's talk about that. What does intelligent life mean? When I say intelligent, what do you think? Tools?
Species like us, maybe.
I mean, are there not many species? Earth alone has, I won't even estimate that the number of species, and has had so many more.
Is it species that are intelligent enough to live on their own?
Intelligent enough to live on their own. I'm not really sure exactly what that means.
Like, they can, I guess, fight for themselves, feed themselves, for the most part, take care of themselves, ensure that they survive.
Perhaps, but would that not require an ecosystem containing other species that they would fight, eat, and survive with? I suppose if you want to put it, the only situation in which organisms do not compete with other species is if we put a man in space. He's got no one and nothing to compete with, does he? But he's still reliant on food items which are based on other organisms, because that's how our metabolism works. He would have had to take that with him, though. Intelligence, intelligent life. What else?
So the conspiracy of Roswell, kind of fake or not?
Let's talk about Roswell conspiracies another time. Let's continue with this line of reasoning first. I don't have an answer for you, by the way. What does intelligent mean? If we hold the standard for intelligence to be someone or something that is capable of thinking and reasoning, using tools, forming culture, civilization, that's kind of a narrow field of view when you think of it, because it's based entirely on ours, which makes it inherently biased. We can't really get around that, though, can we? Because we're the only representatives of what we consider to be intelligence out there. Let me ask you this. Do you know how much more of our brains we use than a chimpanzee? Huh? No, their brains are smaller. If I remember correctly, we use about just a little bit less than 5% of our brains than a chimpanzee do. Or 5% more of our brains than a chimpanzee does. And we have them in zoos. Right? We've driven them nearly to extinction. What if there's another civilization out there that uses 5% more of their brains than we do? What if we're in a zoo right now and we don't know it? Would we be smart enough to see it? Do the chimpanzees? We don't use all of our brains. A vast portion of our brains are essentially giant biological computers. They have electrical impulses. The things that are running through my brain right now causing me to say the words that I want to speak. My brain is delivering electrical impulses to my vocal cords to deliver that sound in the way that I want it to be, that I have learned to make. Every function of my body, voluntary and involuntary, is controlled by that computer in my head. It has neurons that work as circuits. It has specialized cells that work in tandem to hold memory. We are computers. up there. But we only use some of it. About half of our capability of our computer. And this is the subject of quite a bit of science fiction, right? There's a show that I watched for a while. I forgot what it's called. But this guy takes a drug that like activates all of his brain and becomes hyper intelligent. Interesting theory. But the more of your brain that you can use, think of it as having more RAM in a computer. You know how that works? RAM is the memory. When you go to buy a computer, it'll say it has 4 gigabytes of RAM, 8 gigabytes, 16 gigabytes of RAM, right? The more RAM it has, essentially, the larger the bottleneck of data analysis it can do. So like gaming computers, for example, will often have 32 to 64 gigabytes of RAM, whereas something like this has 4. I would never in a million years want to try and play a game on that. It would be so slow. It has a hard time processing my videos for these lectures. But you get a gaming computer with 64 gigabytes of RAM, everything is lightning fast because that bottleneck is so much bigger. The more of our brains that can be utilized, the larger that bottleneck of information gathering and analysis is. I took multivariable calculus to get my bachelor's degree. Most people take it for their master's degree. The college I went to said, you're going to need it for your master's degree anyway, so take it right now as part of your bachelor's. I was like, cool. It was a good choice. I would have needed to take it years later for my master's. But most people take multivariable calculus in college around, assuming that they go through the whole college experience, between 25 and 26 years old. Maybe 25 to 30 if we're being generous with people's timelines. Okay? That's hard. Take my word for it. Maybe some of you will experience it. But what I took at 23, because again, I took it in my bachelor's degree, what if there's a species out there with just 5% more of their brains unlocked? And they learn it in kindergarten, their version of kindergarten. What would that species think of when they look at us? Oh, look at their cute little cities. They built a ship that goes to their moon. Whoa. Oh, but we can't let them leave, right? What happens if a chimpanzee leaves the zoo? Everyone panics. Get the animal control people, tranquilize them, put them back in the zoo. It's kind of a scary thought when you think of it like that. What does intelligence mean, really? And what is its capability? I know I waxed a little philosophical there, but hey, you should be used to that by now. Anything else on that? Or any other questions?
I was looking up that spot.
You were looking up the spot? What about it? What does it say?
They say it's shrinking,
They say it's shrinking.
and they're not sure it might shrink to where it's gone in 20, 30 years, but it might stay, they don't know.
20 or 30 years?
That's the estimate, like,
I mean, for something that's been there for a long time, that would be a very rapid degradation rate. That'd be very interesting.
what causes certain organisms to live longer?
Okay. What causes certain organisms to live longer? Give me an example of one. You must have one in mind.
Some turtles live an average of, what was it, 100 to 200 years.
Yep.
There's some species of jellyfish that can live even longer, and I think the oldest living organism living today is around 1,000 or almost 1,000 years old, and that's related to a plant and bushes.
It's actually older than that.
And that's just for animals. It's even older for some species of plants
Yeah. So if we're talking about individuals, there are some organisms like coelacanths at the bottom of the Philippine Trench, axolotls, which you can find in caverns in the American Southwest, tortoises like the African spurred tortoise, one of which hopefully I'll have later this year, that can live to be 150 years old. If we're talking about groups of organisms that rely on each other to survive and yet are connected biologically, then we're talking about something totally different. The oldest single living organism is Methuselah, a white bristlecone pine. It's about 4,500 years old. The largest colony of organisms that work together to sustain themselves biologically, there is a colony of aspen in Utah that are 80,000 years old. And there is a prairie in Ibiza, Spain, that is about 200,000 years old. And we count this as being one consecutively living organism because they're all joined at the roots, sustaining each other for both the aspen and that prairie. So there's a little bit of a difference between, or there's a little bit of nuance, I should say, to your question here. Having more organisms to feed as a whole is better, apparently. Aspens, meadow grasses. Of course, they require a little less than we do, right? They're photosynthesizing. We require a little more direct approach. We eat things. Our metabolisms are faster. Chemosynthetic versus photosynthetic. Our cells acquire energy differently, utilize it differently, burn out faster. So, not enough of an organic biologist to be able to give you a for sure answer, other than to say oxidization of DNA is a huge factor. There are some organisms that have randomly mutated the ability to replace their cells more efficiently than the rest of ours. Theoretically speaking, certain species of jellyfish can live indefinitely. Some of them may have already, because they regenerate their cells at an extremely rapid rate to be almost exactly the same as the one that they're replacing. Ours suffer degradation over time, and our bodies slow down in the replacement. There are some jellyfish species that can just do it forever and ever and ever and ever and ever and ever and ever. There could be a jellyfish in the ocean, statistically unlikely, it probably would have been eaten by something by now or run over by a boat or something. There could be a jellyfish in the ocean that is hundreds of thousands of years old. A much lower possibility, there could be one that's 1,000,000 years old, right? Theoretically speaking, possible because of the rate at which they replace their cells. Axolotls, interestingly enough, also seem to have a similar ability. While they don't necessarily live indefinitely, they can replace lost body parts because of how rapid their cellular regeneration is. It would be mean to do it, but I could, cut a limb off of an axolotl, and as long as it was able to survive and keep eating, it would be able to grow that limb back to be a perfect replacement for the one it lost. There are people working on how to use that for human limb regeneration therapy. Another example of how fascinating natural sciences are progressing towards human improvement. What else? Abby, Claudia, questions? Supremely confident in their ability to finish this exam. I love it.
Oh yeah, you said life is possible.
Yes.
Would it survive in Neptune as well? Even though it's better.
Neptune has a different atmospheric composition than Jupiter, for sure. And it's much, much further from the sun. It's a lot colder out there. But, like I said, we know that life isn't necessarily temperature dependent. Most of the life that we know about is, but not all of it. So yeah, it is possible out there. Now, the further you get from the sun, the less statistical likelihood there is. But still some. And remember, this is only within the bounds of science and life as we know it. One of my favorite books is written by Andy Weir. It's called Project Hail Mary. Any of you read it? Highly recommend. It is hard science fiction. It is real science fiction. If you're not into science fiction, it might be too much for you. But it's still a great book. Spoilers, right? I hate giving spoilers, but it's pertinent to this topic. He encounters an alien race that is, much to my delight, based upon minerals. Yeah. So instead of having DNA based on amino acids, essentially, the chemical reactions as minerals were forming on their planet had a similar effect towards making signals and storing information in a crystalline framework. And so it essentially made not sentient rocks, but a form of life that stores its information, its genetic information, for lack of a better term, in mineral frameworks. And so it's a whole group, a whole civilization that lives on a planet where the temperature is almost always like 800 or 900 degrees Celsius, right? Hot enough to kill us, but keeps their mineral frameworks fluid enough that they can move and that they can do things like build spaceships, which is how he met them. He ran into one of their spaceships and they had to help each other through a problem, right? Fascinating, fascinating form of life, but not one that is based upon any form of science or conception of life as we can understand it now. And it was just, in the book, it was just as alien for them to think of life forming the way that it did for us. It's interesting because I believe, if I'm remembering correctly, this alien race was like, wait, organic? They're like, the word for organic life can come from that? Because they use it for fuel, similar to what we do. We use organic stuff for fuel all the time. Hydrocarbons, coal, gasoline, right? Methane, butane. All of these different hydrocarbons are organic. Many of them are derived from former life on our planet that is decayed, and the hydrocarbons are a product of it. But it can form inorganically, okay? And that's what they did. This other civilization, if I remembering correctly, used organic compounds for fuel. And they're like, whoa, we never thought that you could use that for life, right? That life could come from that. That's crazy. Think about the ways that we use lithium in our batteries, right? How weird would it be if we found out one day that these metals that we use in our computers and in our batteries could, in theory, had our planet gone a little differently, been the basis of life instead of organic molecules. So life, who knows? Who knows? Would we even be able to tell sentient life if we saw it? Would intelligence, would what we think we are, with what we think of as intelligence, would we even be able to see other intelligent life? I don't know. Maybe there's life living in the electromagnetic spectrum and we just can't see it. Literally can't see it because our eyes are not capable of picking it up. We can only see the wavelengths of light that our eyes have been mutated to see. Dogs see a different wavelength of color than we do. Did you know that? Sometimes when I see a dog barking at nothing, I wonder if it's actually barking at nothing. Can't ask the dog. Great questions. We're getting deep today. Oh, at some point my camera zoomed in on me. Probably when I was waving my arms dramatically at some point. What else?
Will we ever reach light speed?
Will we ever reach light speed? I'm going to optimistically say close. Here's the problem. It's the, there are many names for it. It's the mass fuel paradox. Okay? Is the easiest way to describe it. What do we need to propel ourselves or anything? Energy. What source of energy do we use the most often?
Electrical.
Fuel of some kind. Okay? You require fuel to generate energy for propulsion and the such. That's how planes go. That's how cars go. That's how we go, right? This granola is my fuel today so that I can propel myself throughout the day, right? A rocket will require a certain amount of fuel to propel itself out of our atmosphere. But then even after it leaves our atmosphere, it still has to propel itself through space if it wants to gain speed. Otherwise, it's slowly going to slow. It's going to slow down over time. If I turn off the engines as soon as it's out of the atmosphere, its momentum will carry it for a little bit, but the pull from Earth will slow it down just enough. Eventually, it'll stop and then get pulled back to the Earth, unless it breaks free of Earth's gravitational well. That requires fuel. Now, in space, fuel means something totally different. On Earth, we generate fuel through or energy from fuel through combustion, right? Our cars are combusting, burning gasoline to create the gases necessary to turn the pistons, right? It's making that energy. Nuclear reactors generate heat. That heat heats up water. Coal power plants burn coal to turn to heat up the water to turn the turbines. Combustion of some kind is required. But what about in space? Why does combustion work here? Because we have atmosphere. If I were to shoot an RPG rocket at a car or a plane, it would blow up, right? Big boom, fireball. In space, there's no atmosphere. There's no combustion because there is no gas. There's no gases to burn. So whenever I'm watching Star Wars, you know when you're watching all the original Star Wars movies, like The Empire Strikes Back, right, where they're having the space battles? It's like, big fireball. I'm like, where'd the fire come from? There's no gases to combust out there, right? I appreciate the movies where it's just like they shoot things at each other and then the ship just falls apart, because that's how it would actually happen, right? Because there's no fire, there's no oxygen to burn in space to make a fireball. So when you're in space, the secret to propulsion is not burn gas. It's let gas go. Okay? If you are releasing a stream of particles behind yourself, then you are propelling yourself forward. So often what they will do is they will have liquid gas, what's a liquid gas on Earth, right? Like liquid oxygen, fuel tanks that go up into space. And then they'll release a steady stream of that, and it will turn into gases in space's low pressure, okay? And that stream of gases blasting out of your engine will propel you forward. And then you gain speed. You get that momentum. You're gaining speed, you're gaining speed, you're gaining speed. And guess what? You're in space. There's no atmosphere, which means that there is nothing to slow you down, aside from gravity, but you can calculate for that, okay? Since there's no atmospheric resistance, if I throw a ball, eventually it's going to slow down and fall to the planet. Part of that is because of the gravity of the planet, but most of it is because of the air resistance, absorbing the energy. There's none of that in space. So you just keep going and going and going and going and going, picking up more speed until what? You run out of fuel. And then you're just carrying on at that speed. So if that's how we move through space, how are we ever going to get to light speed? We would have to have enough fuel to propel ourselves through space indefinitely, almost, because I'm gradually going to build up to the speed of light. But here's the problem. The more mass I have, the more fuel I need to propel myself, right? It's easy to understand, isn't it? Bigger ship, more fuel. More fuel, more mass. More mass, more fuel. More fuel, more mass. I never, ever reach the point where I have enough fuel to propel the mass that I need because of the fuel I need. And this is the paradox. According to this current state of affairs, the way that we understand thermodynamics, the way that we understand propulsion and physics, we can never reach the speed of light because we would need an indefinite amount of fuel, which would create an indefinite amount of mass that would need to be propelled by that indefinite amount of fuel. That's the problem. That's the paradox. That's what we can't get around yet. There is a solution, though. Very interesting one. Propulsion, not by the release of matter, but by the absorption of it. Sunlight. Sunlight is photons. Photons act as both a wave and a particle, right? Are we familiar with this concept? Fundamental physics, okay? Photons act as both a wave and a particle, meaning that they have some mass. And that mass contains a very small, minute amount of energy as that light is going through space, right? It has a little bit of it when it hits you while you're suntanning on the beach. It has a lot more in space before it goes through our atmosphere. So what if we could make some sort of sail? This is called a solar sail. These actually already exist. I'm talking about a sheet of gold that is literally 3 atoms thick. I'm talking about you take a coin of gold this big and you flatten it so thin it stretches across a mile. Okay? You flatten that out, you put it on a spaceship. It doesn't look like it's even moving. But slowly, as more and more photons run into this giant sail and give it their energy to that sail, it slowly starts propelling the spacecraft forward. Whatever's attached to that solar sail, it slowly starts moving forward. And because there's no atmospheric resistance, it's not ever going to stop. It's only going to keep picking up more speed. Until finally, theoretically, it can reach the speed of light because its mass stays constant and its speed only increases. There's actually a project right now, and I forget the name. I want to say, was it Messenger? I don't remember what the project name is. But they're putting together, I want like 75 or 100 micro probes. Tiny little things, like this big. Literally just a tiny camera and a transmitter. And their only mission is to be attached to these solar sails. And I'm talking a little box like this big, attached to a sail as big as this building. Okay? Their only mission is to go out to the edges of the solar system, to each planet. There are multiple assigned to planets around our star. They're all going to be sent off in different directions. And they're going to be out in orbit. And it's going to look like they're not even moving for years. And then maybe 5 or 6 years, they're going to be picking up speed. We're going to be like, oh yeah, okay, looking at a telescope, oh, that's further than it was. The next year after that, it'll be way further. The next year after that, we might not even be able to see it. But they're sending their signals back to Earth. And the hope is, by 50, 60 years from now, assuming we haven't developed the ability to teleport or something, or reach the speed of light another way, they will have gained so much speed that they have left our solar system, or they have orbited multiple planets several times. They have gone around our sun. We know so much more about our solar system because of the signals being sent back to us by these tiny little probes that require no fuel to propel. That's the hope. And if that works, if it works for that tiny little thing with a sail the size of this building, shoot, let's make a spacecraft with 5 or 6 people, throw a sail on it 10 miles wide, and send it to Tau Ceti. Right? That might be the next thing we do. That might be how we get around the mass fuel paradox. What else? Huh? What would you do to stop when you reach the speed of light? Oh, that is a very good question. When you're jogging, what do you do to stop? That's a hard question to answer, isn't it? We don't really think about it. We just stop jogging. But really, what are you doing? Ready for a demonstration? I'm jogging. I'm jogging. I'm jogging. What did I do to stop? Watch me again. Don't make me jog more. What did I do? Ah, you saw me lean back there, right? And instead of putting my weight forward on my toes, I kind of put it back on my heels. What I am doing, in physics terms, is applying force in the opposite direction than I was when I was jogging. Using my heels and my toes, the direction of my body, forward and backward, I am now applying force backward, which is canceling out my forward momentum that I've built. How do you do this with a spaceship in space? If we're releasing gas behind ourselves, to generate that propelled energy, we must have the same force pointing forwards now to slow ourselves down. And the rate at which you want to slow down has to be has to be proportional to the rate at which you applied that opposite energy. So if I apply energy that's propelling me 100 miles an hour this direction, after 1 hour, I will have gone how far? At 100 miles an hour, I will have gone how far in 1 hour? 100 miles. Now let's say that I apply force in that direction equal to 50 miles an hour. I still have my momentum going this way at 100 miles an hour, but now I've applied force going that way at 50 miles an hour. So how far will I go in the next hour? 50. Good. I went 100 the first hour, applied opposite force at 50 miles an hour. I went 50 miles the next. I'm slowing down. Then I do it again, and I will be at a standstill by the time I reach this distance after another hour. Okay? I will still go on 200 miles, but the last 100 miles of it, I will have been slowing down at a rate of 50 miles an hour. This is how it works in space. We need enough fuel not only to propel ourselves forward, but also to stop. That's why when you see space shuttles or rockets, you'll notice that they don't just have jets pointed behind them. They also have little jets on the front and on the sides of all these rocket ships and space shuttles so that they can twist and turn in whichever direction they need to go, that they want to go directionally, but also to slow themselves down when they reach their destination. If you ever watch a video of a space shuttle pulling up to a space station, you're going to see a jet of what looks like steam, but it's just gases, being blasted out of the nose cone of that space shuttle so it can slow down and just barely touch the dock. It has to be so mathematically precise. Okay? Now here's the thing. How do you slow down when you have a solar sail? Yeah, we don't know yet. The best case scenario that people have thought of yet is to do so much math. This takes so much math. When you reach your destination, let's say that I am a probe that is meant to go circle Saturn. I reach 7% the speed of light by the time I reach Saturn. I'm going so fast. How do I slow down without any gases to slow me down? if I do my math right, if I'm a space engineer that's done his math right, then I will have calculated the right trajectory and speed at which this probe will get caught in Saturn's gravity, and it shouldn't even need to slow down at all. It'll just keep circling Saturn because now it's caught in Saturn's gravity. And there it remains forever, continually sending us information. Now, the ones that are designed to go out of the solar system, those will never slow down unless they run into something, right? There's only so much we can see out there. The radiation belt keeps some things out. But also, there are bodies of rock out there that are non-reflective. And if it's non-reflective, we can't see it. So it's very likely some probes will leave our solar system and then slam into a comet that we didn't know was there. Some probes will leave our solar system and they'll get pulled into a black hole eventually. Any of you Star Trek fans? No? Okay. I'm a nerd. So there's a plot line from one of the original Star Trek shows, the original Star Trek show, where hundreds of years before, so like in our time now, humans had sent the Voyager probe, which is true. We sent several Voyager probes, right? They leave our solar system and they keep traveling. Well, over the course of the hundreds of years between then and when Star Trek takes place, which is like 2,500 something, right? It's a long time. That probe had encountered an alien race, and the alien race had like done something to it, like done something to its computer, and then sent it on its way, and it gains intelligence. It basically becomes an AI. And then the Star Trek Enterprise and its crew of adventurers are going through space, and they run into this intelligent probe. And I don't remember exactly the plot. I feel like they fought it, like there was some sort of battle, some sort of conflict. And then at the end is when they realize, wait, this came from Earth. We sent this thing off like 600 years ago. And it had taken on intelligence, and it was doing its own thing now, and it was doing that. It was a very interesting idea. Very interesting. It is actually 100% possible, too, that if in 100 years from now we develop the ability to fly at near the speed of light, or even just 10 or 20% the speed of light, we will eventually catch up to that Voyager probe that we sent off in the 70s. We'll pass it. We'll say, see ya, thanks for doing what you did. We'll take it from here. Right? Absolutely possible. All right, any other questions? We've been going at this for about an hour and a half. If there are any other questions, I will happily answer them, though. The probes? Yeah, I believe that they're going to be equipped with small cameras.
So, and it's traveling so fast, at a certain point, are we still going to be able to see what the probes are seeing?
Mm-hmm.
Like,
Because they're sending the signals at the speed of light. Light travels at the speed of light. They're sending signals back to us at the speed of light. So yeah, there's going to be a delay. For example, between Earth and Mars, I believe it's a 36-minute delay.
no, not a delay, but just like seeing it. Wouldn't you be moving? Wouldn't the drone be moving too fast for you to be able to interpret anything that it's seeing?
The drone will be moving very fast, and if we watch it at real time, it'll be very difficult to see. Luckily, we can slow it down, right? Reduce it, take it from 60 frames per second to 30 frames a second. Or 1 frame a second if you wanted to, right?
But then you would miss information too.
You might miss some things, but you capture more than we have now, right? Even our eyes operate at a certain frame rate. You guys seen those 8K TVs that they've got out there now? It's actually a waste of money. Your eyes physically cannot pick up more than, I think, what was it, 4.5, 5,000 K? So while 8K is really impressive, I'll just stick to my 4K screen, thanks, because my eyes can only see what they are capable of seeing. Sure, we make cameras and screens which have a higher definition than our own eyes, but since my eyes are the object that I have to pick them up eventually, there's no point in having a piece of technology that's more efficient than my eyes are, you know? So we can only work with the technology we've got until such a time as we can improve. Maybe it's possible that, I mean, that would be a cool improvement. Develop higher definition eyes. What else? Fun out of the box question though.
How did we take the photos of the black holes?
Take photos of black holes?
How did they get that?
Yeah, black holes don't have anything that we can take photos of, but you know what does? The stuff that's getting sucked in around them. So if this is my black hole, right? Then around the edge of my black hole, there is a halo of all the stuff getting sucked into it. And that's what we see. So more or less, they look like giant rings of matter and light in space. With the black hole in the middle, obviously, unseen. But we know it's there because of the ring of stuff around it that's getting sucked in.
I think I heard someone say it looks like a glazed donut.
It does kind of look like a glazed donut. If I were to erase this, I have it there as black to show you where it was. There's your donut, right? Bless you.
Does it work the same way? I don't really remember what you told us, but it was something about the sun and the planets. Everything around it being like linearly.
Yeah. Yes, it is disc-shaped, just like our solar system. So our solar system grew into this disc shape because of the gravitational influence of the star, right? Black holes do the same thing. So if I'm looking at my black hole like this, it kind of forms this sort of disc shape. We're looking at it from the side. Everything else kind of around it in that disc shape as well. So that's like a top view and that's like a side view. It's just a great way gravity works. It tends to flatten things out. And as it gets flattened out, you get that disc shape. Matter of fact, we call this an accretion disk as things are being pulled into it. They are accreting to each other. What else? Anything relevant to mutation or fossils? It's been a minute since we talked about any of that. I want to make sure that all your questions relevant to the exam are answered. I love answering these, and I won't stop answering them. But I want to make sure everyone's comfortable with the exam too. Yeah.
Not sure it was Pompeii or like somewhere around there. They were like digging out some of the remains from the past. They found like someone's like brain was made of glass.
Okay. So this was not, so he's talking about an archaeological discovery where they found an entire carved head made out of glass. This has happened several times. And if I'm not mistaken, in several different cultures as well, which is a little odd, but not necessarily out of the bounds of possibility. They weren't actually people's real heads. These are carvings from obsidian or quartz that are very, very, very detailed and lifelike. Skulls and head, not copies, but very, very detailed carvings. Someone spent a great deal of time and effort on. It's not outside the realm of possibility that different cultures would be interested in making glass skulls at the same time. But it has led to some discussion about whether or not some of these ancient cultures at different points in time were more connected than we thought they were. It's very possible. Now, some people take it a step further and use it as an alien conspiracy theory. Have you ever seen Indiana Jones and the Kingdom of the Crystal Skull? The what? No. No. The movie, The Kingdom of the Crystal Skull. Probably the worst Indiana Jones movie they ever made. But the whole point of the plot was aliens connected all of these cultures together, and all these cultures worshipped the aliens and communicated to them basically through these crystal skulls. Something like that. I don't remember the exact plot. It was not that memorable of a movie. But that was the point, was because of these skulls made out of glass that had been found, it kind of fed that plot line. You asked earlier about Roswell as well. What was your question with that?
About like was Roswell like the conspiracy of like that kind of fall beach, like what people are saying with that.
Well, Roswell is far from the only place where people have seen weird stuff. Happened a few times in Roswell, and Roswell really leaned into it. I've been to Roswell many times. I know people from Roswell, and they're basically everyone I've talked to who I know from there is in the camp of, we just love the alien thing because it gets us tourists and we make money off of it. Hardly any of them ever actually believe it, but they believe it when there's money to be made, right? Sorry to spill the beans on that, but at least the ones that I've met, the people I've met. You guys ever watched the videos? Like President Trump made them release all of the alien stuff a while back. You guys ever watch any of that? Bless you. It's very interesting. There are some weird things flying through the sky. Some of it may... Was that another sneeze? That was the cutest sneeze I think I've ever heard. Bless you. Some of it actually looks really weird. Some of it could be explained by natural phenomenon. Some of it's definitely man-made. But there are those few things that are just like, huh, what even was that? I don't know what to think about that. It's possible that they are aliens. I've said this before. I honestly, truly do 100% believe that aliens exist. I just haven't seen any evidence that they have been here. At least not enough to compel me. But every now and then, some of those videos that they release that are captured on like military jets, I'm like, that might be man-made, but how would they propel that? Right? So unless someone in the world is like 5 to 6 technology generations ahead of us, which is possible, I suppose, some of those things can't be explained, which makes it very interesting. Most of the alien theories, though, I think are total hogwash.
Because it's supposed to be intelligent. Because they're supposed to, everything they theorize now is supposed to be intelligent.
Who's they?
I guess people that, I guess, the generalized kind of people that think that everything.
Oh, does everyone believe that aliens are intelligent?
No, there's like the stereotype that if you think aliens are real, it's like ones that are intelligent.
Oh, so yeah, you're saying that there's a stereotype that if you believe in aliens, you must believe they're intelligent and they have spaceships. Got it. That's an excellent point. Aliens can exist without having the technology, right? We make so many assumptions based off our own experience. There may have been aliens living on a planet in Tau Ceti for 50 million years and perfectly content to just use spears and live in huts for 50 million years. It's possible that they don't experience mutation the same ways that we do. The eventuality of evolution in the universe is something that we'll discuss another day. But it's possible that they don't experience that, or at least at a much slower rate. Maybe they never developed guns. Maybe they never figured out how combustion works. Maybe fire is not something that happens on their planet, or maybe it's something that they fear because they have an oxygen-rich atmosphere, and fire is much worse for them, right? And so that stunted their technology progression because they don't use fire. Something like that. Any number of reasons why they could look totally different technologically than we do and still have been around for a lot longer. Or been around for a lot less time and progressed much faster. Maybe we're the slow ones, right? Who knows? The potential for both is there. Yeah.
I was saying my question about the crystal skull thing.
Yeah.
I looked it up and it said it was from what they found was a Roman man. They looked in his brain and it was made of glass. They said it was caused by the eruption of Mount Vesuvius.
Oh, I see. His brain had been replaced by ash. The glass from the ash. Very interesting.
They said the volcano turned his brain to glass.
I have never heard of that. That's very interesting. When they say that it turned to glass, what they're talking about is that it more or less turned into an ash tuff, right? As the pyroclastic cloud swept through, body tissues were immolated and the bone probably remained behind, but where the brain was probably replaced by that volcanic glass ash. That's very interesting. I've never heard of that. Very, very interesting. Okay. Well, I think I'm going to call it here. I haven't had any questions relevant to the exam in a little bit. Are we all okay with that? Any last exam-related questions? Right then. The exam will now be opened.